All right, section 2.2 of our calculus text, we're looking at the topic of differentiability. So in this section, we will see how f prime of a, the derivative at some x value, might fail to exist. We'll look at differentiability and how it implies local linearity. We'll look at the numerical derivatives on a calculator. And finally, differentiability implies continuity and intermediate value theorem for derivatives. This video will be on section 221, which is how f prime at some particular x value a might fail to exist. We have no new vocabulary and no new theorems or rules in this section. So we begin with this statement. A function will not have a derivative at some particular point P identified as a comma f of a, where the slopes of the secant lines, defined as f of x minus f of a over x minus a, fail to approach a limit as x approaches a. So here's what we're saying. If we take this difference quotient and put it inside of a limit, the limit as x approaches a, this is the alternative definition of a derivative. If this does not exist, then f prime of a does not exist either. So there's the algebra behind it, but I think what's most interesting is the graphical nature. Inside of the graph of a function, we might see features such as corners, cusps, vertical tangents, or discontinuities, and it's at those places where we're going to say the function does not have a derivative. Therefore, it is not differentiable. So here are examples of those graphs. We see in the top left corner the graph of y equals the absolute value of x. This graph has a feature that we call a corner. As we approach x equals 0, this function comes to a distinct corner point. And what we think about this then is the left and right hand derivatives as we approach 0. All of the slopes of the curve to the left of 0 are -1. All of the slopes of the curve to the right of 0 are 1. And if the left hand and right hand derivatives do not agree at a point, then we do not have differentiability. Furthermore, if you tried to look at a tangent line at x equals 0, you may notice that there is not one unique line. This line touches the graph only at 0, 0, but so does this line, so does this line, and all of the lines in between. So therefore, this one is not differentiable at x equals 0. To the upper right-hand corner, we have the graph of y equals x to the 2/3. This one is similar to a corner point, but we call it a cusp. The behavior is slightly different. If we look at all of the curves, slopes, moving into x equals 0, they actually do eventually agree, except that the tangent line becomes vertical. So in this case, we have, all right, well, if the tangent line looks vertical, that tangent line, well, it's an undefined slope. And if the slope is undefined, well, then we have a derivative that's undefined, or better yet, the derivative, it does not exist. We're not differentiable at x equals 0. Here's a curve that is similar to x to the 2/3. This is the cube root of x, or x to the 1/3. It also doesn't have a derivative at x equals 0, and that is because the one and only tangent line there is indeed vertical. So this one's not differentiable at x equals 0 as well. No slope on that line. The slope is undefined. Therefore, the derivative does not exist. And in cases of discontinuity, we also do not have derivatives. This is the graph of the function y equals absolute value of x over x. We see there is a jump discontinuity. And at x equals 0, first of all, there is no point on the graph. There is an open circle here, and there is no tangent line. Thus, there is no derivative, not differentiable at x equals 0. So here's an example. Find where the function's not differentiable. Find all the points in the domain of f of x equals the absolute value of x minus 2 plus 3, where f is not differentiable. So let's do this entirely with a graphical mindset. We know this is essentially the graph of a parent function, f of x equals absolute value of x. And we already found out in the previous slide that function is not differentiable at x equals 0 because it has a corner point. So here is a nice y-x graph. Here is the absolute value of x, but this function has been transformed. Minus 2 on the inside of the function is going to take us right 2 spaces. Plus 3 on the outside of the function is going to take us up 3. So this graph has been translated to the right 2 spaces and then up 1, 2, 3 spaces. So here is the resulting function. This is f of x. And this then would not be differentiable at its vertex, and that is the point 2, 3. So we are not differentiable at the point 2, 3. Or we could even say something like this function is differentiable everywhere except x equals 2. So furthermore, most of the functions we're going to encounter in calculus are differentiable wherever they are defined. And that means they're not going to have corners or cusps or vertical tangent lines or points of discontinuity in their domains. Their graphs will be unbroken. That's another way of saying continuous. And they will also be smooth. That's another way of saying differentiable. And we bring up this idea of differentiability and what functions are not differentiable so that we're aware of them when they do rarely come up. The functions that we're used to seeing, polynomials, rational functions, trigonometric, exponential functions, and logarithmic functions are all differentiable where they are defined, as are algebraic combinations of functions, such as a polynomial plus a trigonometric function, or composites of differentiable functions, such as plugging an exponential function into a rational function. So most of the functions we will see in calculus are differentiable where they are defined, but in those rare circumstances where we see corners and cusps and vertical tangents and points of discontinuity, we know that they are not differentiable.